Chai. Good afternoon, all. Welcome to the lecture of Lattice Theory. Lattice Theory was actually the third unit of our paper, Advanced Discrete Mathematics. We will just look at the basic definition which are related to lattice theory. The first definition we need to understand lattice is POSET. Okay, we all are familiar about the definition, but just we will recall. Okay, therefore POSET is actually a partially ordered set. Okay, therefore it was defined as a relation R on a set S is called partial order if if it satisfies following axioms. Okay, students also can answer. What are the axioms satisfied by the partial order relation? The first one is reflexive. And what is the meaning of reflexive?
A is
Yes.
related with A for all A belongs to set S.
Yes, it is
A is
related to
related to B.
A. Second property I will write is antisymmetry. What is the property?
If A is related to B, then B is also related to A.
A related to B. Next,
And B is related to A.
B is related to A.
For all AB belongs to the set S.
I think you are missing something. A related to B related to A. It
Then A
implies
equals to B.
yes. This implies A is equal to B for all AB moved out in the corresponding set. And the third property is transitive. Correct na? What is transitive?
If A is related to B and B is related to C, then A related to C.
Yes, A is related to C. In joke, I am always telling students that friendship is a transitive relation, right? Now, I think we have taken also in the class. What friendship is? Friend of a friend is also friend. Now, if A is a friend of B is a friend of C, then A is a friend of C. This holds. But whether the same relation holds for the enemy or dushmani, na? It doesn't hold, na?
No, ma'am.
Because we know दुश्मन का दुश्मन दोस्त होता है, right? Therefore, this dushman is not a transitive relation. Okay, we have already seen many examples in mathematics also, which are having the partial order relation. Therefore, a set yes, together with this partial order relation, a set yes, together with this partial order relation is called as partially ordered set. Together with this partial order relation is called partially ordered set. And in short, we are writing it as POSET, partially ordered set. In short, it is partial. Okay. Just now, someone has told me an example that set of integer z with greater equal is a POSET. Okay. Similarly, set z with less equal, whether it is POSET.
Yes, ma'am.
Yes, ma'am.
Suppose it. Okay. Suppose S is any finite set. I am considering its power set under the relation inclusion subset. Whether it will be a partial order relation, one can
Yes, ma'am.
check it orally. Suppose A is a subset I am taking. A is an element of P of S I am taking, which is a subset of S. Then A is a subset of itself. We are writing always. Therefore, reflexive holds. A subset of B subset of A. Then A is equal to B holds. That is antisymmetric hold. A subset of B subset of C implies A subset of C. Therefore, transitive also holds. Okay. One more example I can give is set Z plus, set of all positive integers under divisibility. Under divisibility is also a POSET. Correct, na? Because a positive integer divides itself.
Yes,
A is
ma'am.
a positive integer, it divides itself, therefore it is reflexive. A divides B divides A implies A is equal to B. A divides B divides C implies A divides C, therefore this is also a partial ordered relation. These are some of the examples we have seen under the POSET. Second definition to understand is comparability. Okay, comparability. What comparability tells us? Two elements of the given POSET are comparable. Okay, before I forget, for this relation, we are using this symbol. It is not less equal actually. So the symbol used for the partial ordered relation. Okay, it was somewhat curly less equal. Okay, so don't get confused with that symbol less equal and curly less equal. This is a partial ordered relation we are using. Okay. Next, comparability. The two elements of the given POSET are said to be comparable. Suppose this S is a POSET. S is a POSET. And what is the relation? This. Okay, this is not less equal. This is a relation, symbol of partial order relation. Then the two elements A and B are said to be comparable. Are said to be comparable if either A precedes B or B precedes A. We are calling this as precedes and succeeds. If this comparability relation holds, the given partial order relation is called as total order relation. And this is called as total ordered relation, and the set is called as totally ordered set. The set is called as totally ordered set, and in short one can call it as a chain. Okay, why the chain word was used? Because if any two elements I can take and those are comparable, that is either A precedes B or B precedes A, that is less equal, you can understand like this also. Okay, then it is going to form a chain like this now. That is, suppose A1, A2, AN are the elements we have in the corresponding set. Okay, then any of the two elements are comparable. Knowing this, we can write a chain like this: A1 precedes A2, A2 precedes say A3, A3 precedes A4, and so on. Say precedes by AN and continue. Therefore, this is what a chain going to construct by the total ordered relation defined on the given set. That's why the another name for this set will be a chain. Okay, I think we have seen this in detail while studying the Han-Banach lemma in functional analysis, right now? Okay, can anybody tell me an example of a chain and not chain also? Example of chain and not chain. Yes? Okay, whether Z plus with less equal is total order or not. What one has to check only that whether two elements of Z plus are comparable with this relation. Okay, therefore if we take any two elements X and Y in Z plus, what the fact is known to us? Either X is less than or equals to Y or Y is less than or equals to X. No other possibility holds. Therefore this partial ordered relation where the elements are said to be comparable, therefore this is called as totally ordered set. Okay, one example we'll try to understand whether that is it is not a chain. Okay, same example I will just continue. Z plus with divisibility. Just now we have seen that this is a POSET, but whether we will check it is totally ordered or not. Whether it is totally ordered or not. Yes, anyone from the students? I'm saying this is not totally ordered. Are you agree with me? Not totally ordered. Any two elements we want to check whether these are comparable under this relation. Therefore here I am saying the two elements are not comparable. Can anybody tell me why?
Because 2 cannot divide 3 and we can't get answer in set of Z plus.
Good. Any two elements, it is not always possible that those are having a divisibility relation between the two. Same example, 2 and 3 if I take. 2 and 3 if I take. We know that 2 doesn't divide 3, 3 also doesn't divide 2. Many examples we can find. 3, 5 also, 3, 7. Many examples we have. Therefore, this is not totally ordered. What will happen if I restrict this to a finite set? Is the same will be true? Let me give an example. Suppose I am taking a set A with the elements say 2, 6, 12 and 36. Purposely I am taking these kind of elements. This is a finite set and I want to check under divisibility whether it is totally ordered set or not. This is partially ordered model. This is partially ordered model. But I want to check whether it is totally ordered or not. For totally ordered, what we want to check? Every two element must be comparable under this relation, divisibility. Now here what we know? 2 divides 6, 6 divides 12, 12 divides 36. Correct now? Right now? 2 divides 6, 6 divides 12, 12 divides 36. Therefore, may I write with this precedes relation? 2 precedes 6, 6 precedes 12, 12 precedes 36 under this divisibility relation. Therefore, this is a totally ordered set. This is a totally ordered set. Let me come to the next point of immediate predecessor and immediate successor. Third definition I will write. Immediate predecessor, immediate successor. Successor I will get first. Immediate successor. Okay. Therefore, let us start with X and with this relation. Less equal I will call be a POSET. Okay. Then for any two elements X, Y in X. Okay. Y is said to be immediate successor of X if X precedes Y and there is no element Z in X such that X precedes Z, Z precedes Y. What is the meaning? Y is immediate successor. Immediate next number you can assume. This immediate successor you can assume. Immediate next number with the corresponding relation. Therefore, Y is said to be immediate successor of X if there is no such a Z between X and Y, then this Y is immediate successor, and with the similar situation, this X is called as immediate predecessor. Predecessor of Y. Just previous element, just previous to Y, just previous to Y is called immediate predecessor. Just next to X is called as immediate successor. Okay. Therefore, this partial order relation we are giving in order to have a clear understanding by an Hasse diagram. Therefore, if we have this partial order relation on a set X, then the Hasse diagram we are going to represent where the vertices of the Hasse diagram represents the elements of X. Vertices are elements of X. Elements of X. Okay. And for any two X, Y in X, Y is immediate successor and X is immediate predecessor. Then Y is taken at a higher level than X. Okay. Y is taken at a higher level than X, and X and Y are joined by the straight line. Let me give you an example so that the idea is clear to you. Okay, X as an example, I am taking a set with 6 elements, and divisibility is the relation, partial order relation. Now we want to draw the Hasse diagram. Okay, now we will discuss first for 1 and 2, whether these two are having a relation, whether 1 divides 2. Yes, 1 divides rather all. 1 divides all, but I will take 1 divides 2 and 1 divides 3, because next 2 divides 4 and 4 divides 2 divides 4 and 2 also divides 6. But what we will do, we will start with the diagram by taking 1 at a lower level. Okay, next I will take 2, 3 and 5 only. Okay, why I am not taking 4 and 6? Because 2 is going to divide these two elements again. Also 3 is going to divide 6. Therefore, the elements I am taking is 2, 3 and 5. So 1 divides 2 I will join. 1 divides 3 I will join. 1 divides 5 also I will join. Next, the elements left are somewhere. Let me draw 4 and 6. Now what is the divisibility relation? 2 divides 4 we will join by a straight line. 2 divides 6 we will join by a straight line. Okay, there is no line between the three elements because there is no comparability between 2, 3 and 5. Next, 3 doesn't divide 4, therefore we cannot draw a line, but here I can draw a line because 3 divides 6. Okay, this is the Hasse diagram for this given set. I think sir has told you about the Hasse diagram of power set. That's a diagram of power set. Power set with three elements. Say power set with the inclusion relation, where S I am going to take the three elements, say A, B, and C. This is also a partial ordered relation. Okay, inclusion is the relation. The first element I will draw phi. Okay, phi is contained in all singleton elements. I'll write as singleton A, singleton B, singleton C. I'm not writing the power set because I'm going to assume that you are knowing the power set. How many elements are there in the power set of this? Yes, three elements.
8 men.
8 elements, right? Where phi is the minimal element, right? That minimal element is contained in all singleton sets. All singleton sets are contained in the doubleton set. What are the doubleton sets? We should write so that inclusion holds. Here I'll mark 3 doubleton sets. Here I'll write say AB doubleton. Here I will write AC doubleton, and here I'll write BC doubleton. Now 5 contained in singleton A. Let me draw a line. 5 contained in singleton B, singleton C. All the 3 lines I have joined. Next, singleton A is contained in these two. No? A is contained in these two. Therefore, let me join this by the line. Now B is contained in these two. This one and this one. C is contained in this and this also. And finally, we left with the original set yes, and all the 3 doubleton sets are contained in the original one. So this is the Hasse diagram for the power set of yes with 3 elements. Okay. According to this Hasse diagram, the idea was very clear. What is the maximal element? What is the minimal element? Which relation, which two elements are said to be comparable? What is the exact inclusion relation, etc. All these things are very clear to us by understanding the Hasse diagram. Okay. Therefore, now we will move to this is a basic we need actually in order to understand lattice theory. Therefore, let me move towards a main definition of lattice. Main definition of lattice. The definition of lattice actually depends upon a partial ordered set, and the definition was very easy. Okay, what the definition says that a partial ordered relation is said to be a lattice if every two element subset has both least upper bound and greatest lower bound, LUB and GLB, every two element subset. Two element subset means what? Between every two elements, we should have least upper bound and greatest lower bound. And if this condition holds, the corresponding partially ordered set is named as lattice. Okay, let me write the definition. A POSET P with this relation. P relation is called lattice. Is called a lattice if every two element subset. Two element subset means between a pair of elements. Two element subset of P has least upper bound and greatest lower bound. That is LUB of XY and xy exist for all xy in P. Okay, and here we are going to denote those LUBs and GLBs with the special symbol as x join y. Okay, therefore x join y is least upper bound of x and y, and we are going to read it as join of x and y, or join of x and y, or x join y. Okay, similarly, the second relation we are going to denote with this symbol, and we call it as x meet y, and this is greatest lower bound between the two elements x and y, and we will read it as meet of x and y, or x meet y. And I will prefer this second statement to read, that is x join y and x meet y. X join y and x meet y. Okay, therefore you have to keep in mind this V-shaped symbol is a join, which gives us the least upper bound of the two elements for every two elements, and ulta V symbol x meet y is giving us the greatest lower bound between every two elements of x and y. Okay, now we will just go to look the simple examples. Okay, the first example we can have is every chain is a lattice. Every chain is a lattice. What is the chain we have seen just now? Every totally ordered set. Okay, that is every two elements are comparable. Then what will be a relation x join y and x meet y? X join y, which is least upper bound of x and y. Okay. If I call this as some relation with x precedes y, then what is the least upper bound between x and y? Yes, if I assume the relation x less than or equals to, because the elements are comparable, and I am assuming this case, x precedes y, then what is least upper bound? X join y? Yes,
Y.
yes, it is y. And what is x meet y? Greatest lower bound between the two elements only. This is x. Correct now? And if we assume the reverse relation holds, that is y is less than or equals to x, then here it should be x and here it should be y. Therefore, every chain is a lattice. Okay, I forgot to tell you another symbol for join and meet. For join and meet, these are the symbol we are preparing. Equivalently, sometimes some authors were using this symbol for join and this plus symbol for meet. Also, instead of writing equivalent, I'll write semicolon. Or sometimes it was star for join and dot for meet. Okay. Now we are going to refer this symbol, join and meet, V and ulta V. Right? Before I forget, I told you the symbols also. Okay. Next, we will take the same example of power set. We will check whether it is a lattice or not. For a power set, yes, with inclusion relation, we will check whether it is lattice or not. What do you think? Will it be a lattice? What do you think? Will it be a lattice, students? Whether it is chain, totally ordered. If it is a chain, then it is a lattice, because already we have written every chain is a lattice. But the point to understand is what is the join value and meet value of this set between the two elements. Okay. Suppose A and B are the two elements of the power sets, that is subsets of SA. Or I can write AB belongs to power set of S. Okay. Then what is an upper bound of the two sets? Upper bound of A comma B. AB. What is an upper bound? Students, what is an upper bound? upper bound is the set which contains both A and B. Correct, na? Which contains both A and B. Okay, and whatever is the least among them will be the least upper bound. And what do you think? What is the least upper bound for these two sets? Sets का विचार करते हैं अपन. Student has to answer me. What is an upper bound for this? Actually, I have answered a half of the question.
Ma'am, is it A union B?
Yes, it is A union B. Okay. Actually, an upper bound is the set C which contains both. That is, A is contained in C and B is contained in C. But what we want? We want least upper bound. We want least upper bound. Now just check how this A union B is least upper bound. Okay. A is contained in C, B is contained in C. Therefore, shall I say A union B is contained in C? Right now. Therefore, this is arbitrary upper bound. And as this relation holds, this is my least upper bound. Correct now? Whether you are understanding this point or not, C, any arbitrary set will be an upper bound if A contained in C and B contained in C. Both the sets, that is a set containing both A and B will be an upper bound. And for least, we are having a criteria, least among them. And we know that if A is contained in C, B is contained in C, then A union B is contained in C. Therefore, this is my least upper bound. What about greatest lower bound? Okay, first, what is the lower bound of A and B? Lower bound of A and B. Some student. A intersection B. You are telling me directly a greatest lower bound, no, actually. Any arbitrary lower bound? Can you tell me? Arbitrary. Here, as I told you, any set C containing both will be an upper bound. Correct. Now here what we want? Any arbitrary set which is contained in both A and B. Correct, na? Suppose D is the set I am writing. Our aim is to find D which is contained in both. D is contained in A and D is contained in B. Okay. In that case, this will be a lower bound. But we know A intersection B is contained in A and in B also. Okay, and if D is contained in A and B, it implies D is contained in A intersection B as well. Therefore, may I write D is contained in A intersection B. Therefore, this is lower bound, arbitrary lower bound, and this will be my greatest lower bound. Correct, no? Please try to understand this fact. Lower bound of A and B will be a set D such that D is contained in A and D is contained in B. Okay. The fact we know is A intersection B is also contained in A intersection B is also contained in B. But whenever D is contained in A, D is contained in B, it implies D is contained in A intersection B. Therefore, according to this relation, A intersection B will be my greatest lower bound. That capital D will be my arbitrary lower bound. Okay. Therefore, here in this case, both LUB and GLB exist. And what is A join B in this case? Is it A union B? Correct now? And what is A meet B? A meet B is A intersection B. And hence one can say that this POSET with inclusion relation is a lattice. Is a lattice. Second example you will try to understand again. Z plus with divisibility. We will try to understand whether it is a lattice or not. Okay. For to understand it is lattice or not, we start with an arbitrary elements A, B in Z plus, and we are interested in finding the least upper bound and greatest lower bound. What is the least upper bound under divisibility? One such element which is divisible by A and divisible by B as well, right now? Upper bound I am interested in finding. Therefore, I want to find out one element, say C, I'll write, where A divides C and B divides C, both holds. But we know that when this holds, if C is the common multiple, correct now? We want to find out one element C which is divisible by both will be the upper bound. And if I take this, it will give us C is multiple of both A and B. In that case, it will be simple upper bound. But I want least upper bound. Therefore, least common multiple will be the least upper bound. Yes or no? I don't know whether you are getting me or not. Correct. Now, suppose I give an example. Suppose I want to find out the join, that is least upper bound of 2 and 3, which belongs to Z plus. Oh, by mistake I have written star. Z plus. Okay. Therefore, what will be least upper bound under divisibility? We want to find out one element which is divisible by 2 and which is divisible by 3 as well. How many elements are there which are divisible by 2, divisible by 3 also? How many elements are there? Divisible by 2, divisible by 3. Common multiple you should tell me, na? 6. Then 12. Correct, na? Is everyone following me or no? I don't know. If all these are the upper bound, and what is the least among this? 6. That is least common multiple. Therefore, least upper bound in the relation divisibility will be least upper bound will be least common multiple, and on the parallel lines I can say that greatest lower bound is GCD of the two numbers, and with this relation this Z plus with the divisibility is a lattice. Okay, whether students are getting this example or not? If you are
Yes,
not
ma'am.
getting this example, you just you can stop me anywhere. Correct. Very simple examples I am considering actually. Now I'll take one example POSET which is not a lattice. We'll take same example. Suppose a set S under the consideration 2, 3, 6, 12, 24, 36. This is POSET with divisibility. I just want to check whether this is a lattice or not. To understand whether it is lattice or not, we must find the least upper bound and greatest lower bound of every two elements. Okay, for most of the elements we can find. For 2 and 6, least upper bound is the least common multiple. The least common multiple is 12, which presents it. For 6, for 3 and 12 also there is a multiple. But for 2 and 3, but for 2 and 3, can we find? Yes, for 2 and 3, 6 is also there. Okay, what for 24 and 36? Whether a common multiple of 24 and 36 exists in the given set? Whether least common multiple of 24 and 36 exists in the set or not? What is the least common multiple of 24 and 36? First question. LCM. See, I am asking you the simple questions of finding LCM and GCD. Students, answer.
72.
72. Whether it is a member of your set?
No, ma'am.
No. Therefore, least common multiple of this pair do not exist. Okay. Now let us go for checking greatest lower bounds. Greatest lower bounds means for GCD. Correct. Now what is the GCD of this same pair? 24, 36. Greatest common divisor of 24, 36. Is it 12?
Yes, ma'am.
Exist? Yes, it exists. Correct, na? Okay. Therefore, we'll check the GLB for all the remaining pairs also, and we'll come to the last pair. GCD of 2, 3. What is the GCD of 2, 3? Greatest lower bound also one can call it as.
1.
Yes, 1. But whether it is present in the given set.
No, ma'am.
We say that these do not exist. Therefore, these two values do not exist, and hence S is not lattice. Okay. Now, sometimes instead of giving the set with the relation, sometimes the Hasse diagrams are given to us, and it is asked to find out whether this Hasse diagrams represents the lattice or not. Correct. So let us try to understand by one simple Hasse diagram. Here is the Hasse diagram drawn like this. The names are A, B, C, D, E, F, and G. Okay, for first we'll try to understand the Hasse diagram. Okay, A is the minimal element. Okay, and A relates B, or A precedes B, A precedes C. Okay, therefore we have written the rule. B and C are not comparable. There is no line between B and C. Again, what is the least upper bound, or what is an upper bound for this B and C? D, na? Immediate successor of B is D. Immediate successor of C is also D. Therefore, this is your least immediate successor of both B and C, that is least upper bound. Okay, likewise we have to understand. Now to check whether it is lattice or not, we will try to find out the closure tables. Table for the both the operations, join and meet. First we will find out closure table regarding join. Okay, this is very similar to the tables we are finding in group theory. Correct, na? To check whether it is closed or not. A, B, C, D, E, F, and G. A, B, C, D, E, F, and G. Now we want to find out join. Join is least upper bound. Actually, here in this case, D is an upper bound of B. D is an upper bound of C. Therefore, this is immediate upper bound. Therefore, this is least upper bound of both B and C. Therefore, this will be the value of our join. Okay, we'll try to start. Okay, first A join A. What is A join A? Least upper bound of the pair A comma A. Can anyone answer? Students, least upper bound of A and A do not exist. Correct, na? Least upper bound do not exist. Is it the same answer? Is the screen visible to everyone? Why no one is responding?
Ma'am, how to compare that? How should I compare?
See, whatever same element you are rating, na, least upper bound of 2 and 2, whatever it may be the relation, it's 2 only. Same element, no, therefore it is A. Correct, na? Suppose I will write A less equal by A under this less equal relation. What is the least upper bound?
A.
A. Number itself, na? The point is to think if we have two different elements. Here we have same element. Okay, now we'll think for the next. Now what is A join B? Now look at the sketch. A and B, there is one line where it shows that A is immediate successor of B, or B is immediate successor of A. Therefore, what is this relation? If I write like this with relation A, partial order relation B, A less equal by B is this kind of relation. Then what will be the least upper bound among the two? Two elements I have only with this relation. Then what is the least upper bound between A and B? This is B, na? Correct, na? Are you getting confused? Suppose 2 less equal by 3 is the relation holds, and I am asking you what is the least upper bound of 2 and 3? This set. 3 only. Correct, na?
Yes.
Similarly, is someone asking me a question? Hello. I hope I am clearly audible.
Yes, ma'am, audible.
Is this point clear? 2 less than or equals to C. If I write a double turn set 2, 3, what will be a least upper bound? 3 only, na? Here A is a predecessor of B. B is successor of A. Means B will be a least upper bound among the two. Correct? I cannot say D is a least upper bound between. If I want to write this, D is not a least. This is not immediate successor of A. D is not immediate successor of A because B is in between or C is also there in between. Correct, no?
Yes, ma'am.
Yeah, what for A and C then?
C, ma'am.
C. What for A and D then?
D.
कोण मोठा असेल थोडक्यात?
D.
Asking least upper bound. I just want to know. Here according to the Hasse diagram, A precedes B, B precedes D. Correct, na? A precedes B, B precedes D. Therefore, surely A precedes B. Correct, na?
Yes, ma'am.
Therefore, what is the least upper bound among the two?
D.
D, right? What for the remaining shall I write? As it is. E, F, G. Correct, na? Okay. Now let us start with the second row. B and A. What is the upper bound? Least upper bound. B and A. Already we have written A and B is B. Therefore, B and A is B. What is for B and B?
B.
B. B and C. B and C. Least upper bound is
D.
D. Correct, na?
Yes, ma'am.
B and D.
D.
D. Right, na? D you are saying. वरचे एलिमेंट्स लिहित जायचं थोडक्यात. What is B and E? E. Yeah. G. Okay, next. For C, C and A, C. C and B, D. C and C, C. C and D, D. C and D remaining as it is. If you have still a confusion, you just stop me and ask. D and A. D and A. Upper bound.
D.
D, na?
Yes, ma'am.
What for D and B? D and B. Upper bound. D. Correct. What for D and C? This. D again. What for D and D? So D. For D and E, now it's E. Correct, na? Least upper bound you have to understand by the Hasse diagram. If the Hasse diagram concept was very clear, then only you can understand this. Otherwise, it's not difficult. Okay, what for E and A?
E.
E.
E. E and B.
E.
E. What for E and F? What for E and F? G.
G.
Correct, na? What for E and G?
G.
G. Okay. F. F and A. Yeah.
F.
F and B. Yeah. F and C. F and D. Yeah. F and E. Now think. F and E I'm saying. Yeah. And E. What is the upper bound? G. Correct. F and G. Sorry, F and F. F and F. Yeah. F and G. G, na?
Yes, ma'am.
Last, G. Nothing to think. Correct, na?
Yes, ma'am.
Only to think. Therefore, here if we observe the join for every pair of elements exists, therefore one condition satisfied. Now we will just think whether need exists. I rewrite that diagram. Okay, now we will write for need. Need means lower bound now, greatest lower bound we have to think. Greatest lower bound. A, B, C, D, E, F, and G. A, B, C, Now students has to answer these questions. Okay. A and A, no doubt A. A and B. Upper bound now we are thinking. Least upper bound.
A.
Sorry. Greatest lower bound we are thinking.
Mm.
Greatest lower bound. A and B. What is the lower bound?
A,
Here the
ma'am.
relation holds A precedes B and we are interested in the lower bound. A is the lower bound. No other element is less than A. Therefore this will be the greatest. Correct. So between A and B, A holds
Yes, ma'am.
A and C.
A.
A and D now. As here we have not, as this last line we have written, or upper bound as G throughout. Therefore, for first lower bound, nothing to think. The greatest lower bound will be A itself.
A.
Correct, na?
Yes,
Now
ma'am.
for
Yes, ma'am.
B meet A. B meet A. A.
A.
B meet B. Hmm.
B.
B. B meet C. B meet C.
A.
B and C lower bound is A. Correct. Next B and D lower bound B and D. B na.
Yes, ma'am.
B and E.
B.
Now nothing to think again. Okay. C and A. A.
A.
C and B. C and B. A. C and C. C. C and D.
A.
C and D. Between C D. C
C.
na.
Mm.
C and C. Okay. Is it clear for C and D how it is C? A
Yes,
will
ma'am.
not be there. Next for D. D and A. D and A lower bound is
A.
A.
D and B.
B.
D. D and C.
C.
C. D and D.
D.
D. No, no. D and E. Here it is. It's D. D and F.
D again.
D again. D and G. D again. Next. E and A.
A.
This is E. Here it is. Yes. E. E and B. B. E and C. C.
Mm.
And D. D. E and E. E. E and F. E and F. Now think. E and F. Common predecessor exists, which is E.
D.
Right. E and G. E and G.
E.
E. Good. F. F and A. A.
A.
F and B. B. F and C. C. F and D. D. F and E. Now think. F and E and say. Common exists, which is D.
D.
F and A, no doubt here. F and G.
F.
F.
Now G. A. B. Correct, now. C. D. E. F and G. Correct?
Yes,
Therefore,
ma'am.
here for every pair meet also exists. Therefore, this is a lattice. This is a lattice. Now I'll give the homework. Another two Hasse diagram I'll give you just. Okay, you have to prepare both the tables. A, B, C, D. One more I'll give you. A, B, C, D, E, E. Here it is here and G. You have to check whether both the diagrams, Hasse diagrams, represents a lattice or not. Okay, and we will continue the properties of lattice theory in the next lecture. If you have any kind of doubts, you can ask me. Some students say, Today we have introduced only the definition of lattice and the examples we have seen. How to solve the examples by using a Hasse diagram as well. In the next lecture, we will go for understanding the properties of lattice. Okay. Thank you for watching the lecture.